the math that Enrico Fermi did to avoid blowing up Chicago. He was supposed to build the world's first nuclear reactor. They collected the 93,000 pounds of uranium and 800,000 pounds of graphite that they would need. Fermi recorded the number of neutrons per minute hitting an indium foil detector at the center of the reactor. At 54 layers, the sensor reached 12,400 neutrons per minute. The whole purpose of a nuclear reactor is to sustain a nuclear chain reaction, where the number of neutrons being created is equal to the number of neutrons absorbed or leaving the reactor. This condition is known as criticality. To compute when the reactor would go critical, Fermi divided the radius of the reactor squared by the neutron intensity A, and tracked this metric as his team built the reactor. Fermi knew the pile would go critical when this metric reached 0. Fermi's math works because... I have no idea. Seriously, I've scoured the internet. I would like to figure out how it works. So yeah, can you help me, right? Can you help me figure this out? I really don't know the answer. I have some guesses, but I would love some help.
Right, so we have this Fermi problem that you have posed. Now, I have not done my due diligence, so I haven't really read through those reports. I probably should have. I should also have an iPad with a pen input, not just my fingertip. But, right, so what he does is he plots the radius of his reactor squared divided by his neutron intensity. So, right, what does that mean? Well, if we assume a sphere, and this is kind of very difficult to draw a sphere. I hope that makes sense. That's our value, or for radius. So, well, what he's doing with r squared is, right, r squared is proportional to your cross-sectional area. And that's easy, right? It's easy for him to measure the radius of his reactor and use that as r squared as a surrogate for the cross-sectional area. His other thing is neutron intensity A, right? So neutron intensity, right? He gets that from his detector. That's what he measures. And what that really is your... I can't spell. Very sorry, but that's neutrons per area, right? So neutrons are subatomic particles. You can't just count the number of neutrons and say I have X amount of neutrons per unit area. But what he can do is he can look at the reading on his detector and say I've doubled my detector reading, my neutron intensity has therefore also doubled. So the most obvious thing to do here, right? The most straightforward thing would be multiply the two, right? And what does that give you? Well, let me extend this border. What that would give you is, that would give you area multiplied by neutrons per area, which would just give you the number of neutrons. Now, why does he not just use this, right? Because that would be specific to this setup. Right, so the number of neutrons you need for a criticality is specific to your setup. So as soon as he adds another layer or changes the reactor somehow, that value needs to be changed as well. So that doesn't tell him something very useful, right? What he's really interested in is the state of this variable A, his neutron intensity. He wants to know if that is increasing with time with respect to time, right? That's what he wants to know. Or, so if his neutron intensity is increasing with time, that means he's supercritical. He's, getting a chain reaction. And if it's, decreasing with respect to time, he's subcritical. So it's going to fizzle out. It'll generate a bit of heat, but it's going to fizzle out. What he wants to know is that it's stable with respect to time. Now, for obvious reasons, he can't actually just go and build a reactor and then say, oh, great, we're supercritical, and then blow himself up. That he's not going to do that. What does he do? Well, his influence factor is the radius, right? So the larger the reactor, the more the neutrons it captures. So the neutrons can't escape a larger reactor. So that's why he's interested in his r squared. And he plots it against his neutron intensity. So we'll give these fake values just to make it simple. So I'll say 100 divided by 1,000 and that'll give you 0.1. Now, if we have our same radius, but we now have 1,000 times higher neutron intensity, we'll get this. So you can see that this is trending towards zero for criticality. Okay, so I just had a bit of time there to finish this off, and so we can see it trends to zero as we reach criticality. Next, I have some toy data I created. Quite literally, just made it up. So what I'm gonna do to tie all this together is just try to recreate that graph that Fermi plotted. So yeah, so we pick our pen, and we'll start at 100, and then this can be 0. And this quantity is going to be our R squared over neutron intensity. And then this is our initial value. This is going to be plus 50, and plus 50. So just to explain this toy data, right? So for the radius, right, it increments a fixed amount or a layer each time. So we can see that on the top. And then the bottom line of our division is our neutron intensity. And now that's exponential growth. So we can see it doubles. So we have 5, 10, 20, and 40. So that's our exponential growth. And while our cross-sectional area is just incrementing by a fixed amount each time we add a new layer. So Fermi called this layers with an S. And really that's just a surrogate for size, but we know that's proportional to R squared. So we'll put R squared in brackets, right? So we have our original 500, and in each increment we add plus 50. So what happens if we plot this, right? Well, the first one we get is an X up here. So we're at, 500 is a cross-sectional size, and we have 100. Next is we're down to 55, halfway down. Next we're a third of the way down, and 16% of the way down. We start looking at this. I have to extend my graph. So here we have that graph, and then you can extrapolate it. Now the thing about this is it never actually reaches zero. So it's what the mathematicians call asymptotic, because both R squared, right, the cross-sectional area has to be bigger than 0, and then the neutrons per area is also positive as well, right? You can't have negative area or negative neutrons per area. So that never actually reaches 0. So you need some acceptance criteria for when criticality occurs, I guess. But that's his graph, and by fitting a curve to your data points, that's how he can predict when he'll reach criticality. And that's why he said at 0 you get criticality, because our neutron intensity skyrockets exponentially.